Okay, guys, once again, I'm going to go over some problems that are like the limit problems I assigned you for this week. Um, Once again, you do not need to watch this whole video. I mean, you can, but it's really just here to help you in case you get stuck. There's a lot going on here, so just watch the video if you need to. Anyway, let's begin. We're going to talk about limits here, you guys. This whole section here is about limits. And what I've done is I've broken up your guys' worksheet into types of limit questions, and that's kind of a nice little summary of how to find limits. Um, so I'll be posting this in this week's video. If I forget, somebody remind me. I'll gladly repost it. But it's something you probably already have in your notebook, but if not, just let me know. I'll send it your way. But I'll be posting it this week's work if you want it. It's just a nice summary of how you find limits. So how do you find limits at x equals c? Well, you always try direct substitution works. If it doesn't, if you end up with something that's undefined, which is usually what would happen, by the way, very rarely do they work by direct substitution, but you want to try it first, because that way you know if you need to do low, be tall. So it's worth a try. But anyway, if it doesn't, there's basically 5 different cases that I want you guys to be aware of. First of all, if you have a polynomial over a polynomial, just do low, be tall. You can factor it and cancel out what they have in common, but it's kind of unnecessary. I would just say do low, be tall. If low, be tall applies, which it probably would. You would have to get 0 over 0 or infinity over infinity. Next thing is if you have square roots involved. If you have that, you're going to be rational, which I will refresh your guys' memory on how to do that when we get there. If you have a complex fraction, fraction side of a fraction, usually all you need to do is simplify it. And then just so you guys know, with a natural log, you're probably going to end up using L'Hopital. The only thing you really need to be aware of, though, is that you need to know what the graph of log looks like to understand this. Log looks like this. So if there's my x and y axis, log looks like this. And basically, what this limit here is saying, it says that as you approach 0 from the right side, the y value goes down into negative infinity. Okay. So keep that in mind. That might come in handy. Another thing is e to the x. If you have e to the x involved, it's probably another L'Hopital. Now, if none of these things apply or none of them work to actually give you an answer, then it's what we call Then it's what we call a non-removable discontinuity. Okay? And when you have a non-removable discontinuity, all you can do at that point is use a table to see what it's approaching. So as you get closer and closer to this c value, what seems to be happening? Are the numbers getting bigger and bigger or more and more negative? In other words, is it becoming positive infinity or negative infinity? And if it's doing the same thing from the left and the right, then you can say infinity or negative infinity. But if it's doing opposite things on the left and right, then we simply say the limit does not exist. Okay, there's a lot going on there, but all the examples we're going to be looking at later on will summarize that. There's also some things to consider when we get to limits at infinity. I'll try to come back to that when we get there. I don't want to talk too much for now about that. Let's go ahead and jump in and try some limits as x approaches some particular. All right, so for number 1, you always try direct substitution first. So let's do that. If I plug in -1, I get 2 times -1 plus 5, which is simply 3. That's a good answer. It exists and it's 3. That's simple. You always try direct substitution first. Let's take a look at another one. Complex fractions. It goes from being super easy to something a little bit uglier. All right, how do we deal with complex fractions? That means when you have a fraction inside a fraction. Well, first of all, you may notice that direct substitution is going to cause a problem. If you did direct substitution, when you plug it in right here, you're going to end up with -1 plus 1, which is 0. And that's going to end up giving us 1 over 1 over 0 plus 1. And this is a no-go. You can't have a fraction with a 0 in the denominator. So direct substitution fails. So when you have a complex fraction, the way you deal with these ones is by simplifying the fraction. What I'm going to do is I'm going to multiply every term by the little denominator there. So I'm going to multiply the top here by -1 plus x. And the reason I'm going to do that is because that's going to cancel these out now, right? Since I multiplied this particular little fraction here by -1 plus x, you have to multiply everything by -1. So I have to multiply this one over here by -1 plus x, and I have to multiply this one here by -x. Okay, so let's see what we get as a result of having done that. On the top now, if I distribute this inside, I'm going to get -x plus x squared. And on the bottom, I'm going to have this 1 left over, plus, if I distribute the 1 here, -1 plus x. Now, these two 1s cancel, right? So now I have this. Okay. So now what we can do is we can try to do our direct substitution once again. And let's see if that works. So if I do direct substitution this time, I end up with -1 plus 1 squared over 1. And there's nothing wrong with that answer. That's going to work. That's going to give me something good. I have -1 plus 1 on the top, which is 0 over 1, which is 0. There it is. So the trick here is what we did in pink. When you have a complex fraction and direct substitution fails, all you're going to do is you're going to multiply everything by the little denominators to write a simpler expression. And usually that'll take care of the discontinuity. That's, by the way, whenever you get something that's not allowed, that's called a discontinuity. And these little tricks we're doing that make it possible for us to do it is called removing the discontinuity. They're called removable discontinuities. However, it's possible you may end up with a non-removable discontinuity, which we'll get to a little later. For now, let's go ahead and take a look at the next one, radicals. Now, if I did direct substitution right now, you guys see how I'm going to get 0 in the bottom? So if I did that, I'm going to get a discontinuity. That's not allowed. So we need to fix this. We need to remove the discontinuity if possible. And when you have a square root involved, you're usually going to end up doing something called multiplying by the conjugate. All right? So what is a conjugate? Before I begin solving this problem, I want to remind you guys of what a conjugate is. A conjugate is this. These are what we call a conjugate pair. They're the same thing, it's just that they're opposite signs. Now, when you multiply these things out, you get x times x, which is x squared, and you get a times a, which is a squared with a minus in between. Okay. You also get a times x and x times a, but they're opposites and they just cancel each other out, so we don't include it in the answer. So this is our answer. Now, why is this helpful when we have square roots? Well, if you have a square root involved, when you multiply square root conjugates that have square roots, you get this. And what's cool about that is the square root cancels out, and you no longer have a square root. So that's the strategy we're going to apply here, is we're going to multiply by the conjugate. So this is like your first term, and this is your second term. So I'm going to multiply the top and the bottom of this fraction by a conjugate of the top. Now, it's not always a conjugate of the top. It's a conjugate of wherever the square root is, just so you know. So here's my first term. Here's my last term. And instead of having a minus in the middle, we're going to have a plus. Okay? And that's the conjugate of the numerator. But whatever you do to the bottom, you have to do to the top. Or whatever you do to the top, you have to do to the bottom also. So now I'm going to put this here, bottom as well. Okay. Now, on the top, something pretty cool happens. We do the first two multiplied together, and anytime you multiply a square root by itself, you get the same expression. It's just that the square root goes away. So now instead of square root of x minus 1, I just have x minus 1. We also multiply the last two together. It's 1. And since we were multiplying positives and negatives, it's a minus 1. On the bottom, we're not going to really do anything. We're just going to leave that as is. Okay, now next, let's go ahead and simplify the top a little bit more. X minus 1 minus 1, that can be simplified into x minus 2. Now what's kind of cool about that is those cancel out. And so now I have the limit as x approaches 2 of 1 over square root of x minus 1 plus 1. So now we've done our strategy. We multiplied by the conjugate and we came up with a different expression. Once you've done that, go ahead and try direct substitution again. Computer's writing things up. There you go. So now it works. So there's your strategy. So when direct substitution fails and you have square roots involved, you're going to multiply by the conjugate on the top and bottom, and you're going to simplify, which should end up canceling something out. It should remove the thing that was giving us a discontinuity before. It should get rid of that. And then when you're done, you just do the direct substitution again, and there shouldn't be no more discontinuity because it got removed. Okay, so that's the strategy when you're dealing with radicals. Go ahead and move on to another question here. Now, this problem can be solved in two ways. One way is with factoring, and the other way is with L'Hopital. And I just think L'Hopital is easier, so we're going to go with L'Hopital. But you have to remember, you're only allowed to use L'Hopital if you get an indeterminate form of 0 over 0 or infinity over infinity when you do your direct substitution. If you don't get one of those, like you can't have 0 over 5. Well, if you did, you have an answer anyway, it's 0. But you couldn't have this, for instance. You couldn't have infinity over 2. That's not an indeterminate form anymore. There's actually an answer for that as well. It has to be 0 over 0 or infinity over infinity in order to use L'Hopital. And just so you guys know, the signs don't matter for the infinity over infinity. It could be positive infinity or negative. It doesn't matter. All right, so here we go. Let's do direct substitution. So if I do direct substitution, on the top I get 0. And on the bottom I get 9 minus 15 is negative 6 plus 6 is also 0. So it yields, we're not going to say equals, because 0 over 0 is not a number. You can't say it equals 0, 0. But we can say that direct substitution, I'll abbreviate that DS, direct substitution yields 0 over 0. Therefore, by L'Hopital, there's supposed to be an S. I always leave that out. We're going to find the derivative in a different way. We're going to say that the limit as x approaches 3 of x plus 3 over x squared plus 5x plus 6 is the same thing as the limit as x approaches 3 of, take the derivative of the top, take the derivative of the bottom. That's L'Hopital's rule. Before I go any further, if direct substitution gives you 0 over 0 or infinity over infinity, you're going to say, oh, direct substitution yields an indeterminate form. So by L'Hopital's rule, the limit we're trying to find is equal to the limit of derivative of the top, derivative of the bottom. Then you go ahead and do your direct. And I made a mistake, so I had to go back and fix it here. So where I left off was I was saying that at this point we can go ahead and do the direct substitution with this new expression of 1 over 2x plus 5. And at this point, you can do your direct substitution. So you're going to plug in your negative 3. And negative 3 times 2 is negative 6 plus 1 is 1. So final answer, negative 1. Okay. Now there is another way to do these problems. And if you don't care, you can fast forward it. For the most part, it's not really going to be in that L'Hopital does it anyway. It's easier in my opinion. But the other way to do this is by factoring. The top doesn't factor, but the bottom does. The bottom factors into x plus 3 times x plus 2. And these cancel. And then we just do direct substitution. So you still end up with 1 over negative 1, negative 1. All right. Moving on. More L'Hopital. These are just trig problems. So I'm going to treat them a little bit differently, but they're pretty similar. So direct substitution, if I do that, I'm going to get 0 on the bottom, which is not allowed. So, and also, if you plug in 0 up here, you end up with 1 minus sine of pi over 2. Sine of pi over 2 is 1, and so you get 0. So you end up with 0 over 0, and therefore, by L'Hopital, we could say that the limit above is the same thing as the limit of the derivative of that expression on the top and bottom. Oops, erased. Clean this up a little bit. So the derivative of the top, the derivative of 1 is 0, so we don't really need to write that anymore. It just goes away. The derivative of sine is cosine, so we have negative cosine. The negative is going to stay there. And then the derivative of the inside, we need to multiply this by the derivative of the inside also. The derivative of the inside is going to be negative 1. So if you multiply this by a negative 1, it ends up being positive 1 again anyway. And the derivative of the bottom is 1. So now we're going to go ahead and try plugging in 0 again. So now if I plug in 0, I end up with cosine of pi over 2, which is 0. And we're done. So direct substitution gives me an indeterminate form. So I took the derivative of the top, took the derivative of the bottom, did direct substitution again, got 0. All right, moving on to another one. This one's the same kind of problem. Just another example if you want to see one. So if we plug it in, we get 0 on the top. Plug it in, we get 0 on the bottom. So therefore, this limit is equal to the derivative or it's equal to the limit of the same expression, just derivative on the top, derivative of the bottom. Derivative of the bottom is easy. It's 6x. Derivative of the top is a little bit uglier. First of all, sine squared of 3x. A better way to write that for calculus would be like this. And you guys can see we actually have a chain rule. It's actually a double chain rule. When we learned this, we compared it to an egg. We have yolk on the inside here, 3x. We have our eggshell here on the outside. And then we have sine x is like the whites of the egg. All right, so when you're doing a chain rule with double chain, you just do the derivative of the outside first. So move 2 to the front. Don't change the inside. Take 1 off the power times the derivative of the next one, which is the egg whites. So the derivative of sine is cosine. Don't change its inside. Times the derivative of the yolk, 3. So if I were to simplify this whole expression, what I would end up with then on the top of my fraction would be 2 times 3 here would be 6 sine 3x cosine 3x. 6's cancel. And we can just try our direct substitution again. So direct substitution here gives me 0 on the bottom again. Darn it. Plug in 0 on the top, we get 0 here. Plug in 0 here, you're going to get 1, but it doesn't really matter. We still end up with 0 over 0. So guess what? We're going to have to do L'Hopital again. Sometimes you have to do L'Hopital twice. So I'm going to erase this and make some room for myself. Here's what we had. Oh, this cancel. So now we're going to, since we got 0 over 0 again, we're just going to do the derivative again. And the derivative at the bottom is pretty easy. That's just 1. Top is going to be a problem. We have a product rule, and it's a chain rule as well. So I'm going to call the sine 3x a. I'm going to call the cosine 3x b. Product rule is ab times ab plus ab. Derivative of the first, derivative on the other one. So the derivative of sine 3x is going to be 3 cosine 3x. Remember, it's derivative of the outside times derivative of the inside. The derivative of sine is cosine. The derivative of 3x is 3 times b, which is cosine 3x, times a, which is sine 3x, times b prime. So the derivative of cosine 3x, the derivative of the inside is 3. The derivative of the outside is negative sine. Okay, so there's our derivative. Now we don't really need the 1 on the bottom. I'm going to erase the a and the b too, because they just don't need to be there. Erase my little bars. But all we did was the product rule, really. Now we're going to try plugging in 0 again. So plug in 0 here. 3 times 0 is 0, and cosine of 0 is 1. So we have 3 times 1 times another 1 plus, plugging in 0 here, 3 times 0 is 0, and sine of 0 is 0 times negative 3 times, plug in 0 here, you get 0 again. All that's just 0, so we don't pay attention to it, and the final answer is 3. Okay, so that was an example where you had to do L'Hopital. All right. Now we're going to start talking about limits at infinity. So I'm going to pause my example problems here for a second. We're going to talk about some stuff pertaining to limits at infinity. How to find limits at infinity. All right. Now technically, this is like a polynomial over a polynomial once again, just like we had earlier. But slightly different rule. By the way, just so you guys know, L'Hopital will work for this as well. But there's another way that's faster. Okay, I'll demonstrate one when we get there. But if you have a polynomial over a polynomial and you're finding a limit at infinity, then if you have a polynomial over a polynomial, here's the fastest way to do it. If the power on top is less than the power on the bottom, then the limit at infinity is 0. If the power on the top is equal to the power on the bottom, then the limit will be whatever these coefficients are written together as a fraction. If the power on the top is greater than the power on the bottom, then your limit is either going to be positive infinity or negative infinity. And the only way to kind of figure out which it is by probably just doing L'Hopital's rule or plugging in really big numbers to see whether you end up with positives and negatives. But we'll get to those examples when we get there. Now, if you have trigonometric limits at infinity, you're going to have a few different possible outcomes. First of all, just so you guys know, trigonometric functions oscillate. They go up and down like this, or they go like this. Either way, they never stop going up and down, and therefore, as you go off into infinity, they don't reach a limit. They always wiggle up and down. They don't reach a particular value. They oscillate. So we say the limit does not exist. Now, just so you guys know, a lot of times, though, when you're doing these limits of trigonometric functions at infinity, you have more than just a trig function. You have a trig function that's either being multiplied or divided by something. So if you have a trig function that's being multiplied by something and that other thing comes out to be 0 at infinity, then that's 0, because 0 times anything is 0. Or if you have an oscillation and you're multiplying that times infinity, what that means is the limit doesn't exist, because what happens is you're oscillating and it's getting bigger and bigger. It's getting more and more infinite, and it never stops increasing or decreasing. Also, if you have an oscillation being divided by infinity, it goes to 0. Anytime you divide by infinity, it goes to 0. But once again, that only applies to sine and cosine. If you have an oscillation divided by infinity, but you're dealing with tangent, cotangent, cosecant, or secant, dividing by infinity doesn't exist. Now the reason for that is because when you divide by a really big number, the values get smaller and smaller. Okay, and so your function's wiggling for sine and cosine, but getting smaller and smaller, so it actually reaches a limit of 0. But when you're dealing with these guys, they don't wiggle in the same way. They actually go off into infinity themselves, and so dividing by infinity results in an indeterminate form, and it's just not really answerable. So we say the limit doesn't exist. And if you ever have infinity over an oscillation, that doesn't exist. Okay, so if you have a number that's getting bigger and bigger on the top, dividing it by some number that's going back and forth and changing, the outcome's never going to reach anything. That's for trig functions. And we're going to be solving these with L'Hopital. For Ln, you're going to solve L'Hopital once again. And we talked earlier about the graph of Ln. Ln looks something like this, right? If you're going off into infinity, as you can see, the graph just keeps going higher and higher and higher, very slowly, but it does. So it goes to infinity as x goes to infinity. Now the e function, though, is a little bit different. E looks like this. Okay. Now at infinity, meaning as you go to the right, it goes up forever. So that's infinity. But at negative infinity, that means as you go to the left, as I go this way, it approaches 0, a horizontal line. So that one's a little bit different. Okay. I have some other facts here that will probably come in useful along the way. Infinity plus a number is just going to be infinity. Infinity minus a number is still infinity. But if you have a number and you take infinity away from it, you end up with negative infinity. Infinity times a number is infinity. Infinity times a negative number is negative infinity. Here, negative infinity times a negative number, it's positive infinity. We talked about these ones already. Infinity being multiplied by an oscillation does not exist. We won't say it's infinity, we'll say it doesn't exist. And that's because the infinity is being multiplied by something that's going up and down. So it could actually just be going up and down itself, going from positive infinity to negative infinity. Infinity divided by an oscillation, we talked earlier about that already too, it does not. But an oscillation divided by infinity is actually 0, if it's sine or cosine. Right? If it's tangent, secant, which, by the way, the only reason why I'm writing only this one is because that's the one you usually see. They don't usually do the tangent. Possible. Infinity divided by a number, still infinity. But a number divided by infinity is 0. Think about it. If you take a number and you divide it by a huge number, the outcome is very small. And the bigger this number comes, the smaller it gets, so it approaches 0. All right. So, keeping all that fun stuff in mind, that's limits at infinity. I'm going to show you guys how to deal with those various types of questions. were. All right. So now this is a polynomial over polynomial. There's an easy way to do this, and there's a little bit more of a difficult way, but the cool thing about the difficult way is it's easy to remember. The easy way is hard to remember, but if you know it, it's easy. Okay, now on our slide, we talked about how when you're dealing with limits at infinity, which is what this is, it's a limit at infinity, and you have polynomials, what we said about those was that if the number on the top, if the exponent on the top is equal to the exponent on the bottom, the limit is just the fraction of the coefficients. So in this case here, since 2 equals 2, that means it's just going to be this coefficient over this coefficient, and we don't want to leave out our negative. The 4 doesn't matter. So the answer is -1. Now you can also solve this problem using L'Hopital. Okay, using L'Hopital, we could do this. I could plug in infinity, and if you square infinity, you get infinity. And if you square infinity, you get infinity plus 4, which is also infinity. So we end up with negative infinity over infinity, and that's L'Hopital. So what we would do is we would take the derivative of the top and the derivative of the bottom. Right? The x's cancel. -2 over 2 is 1, -1 I should say. And anytime you take the limit of a constant function, the answer is just that number. Now if you don't know why that is, it's because think of the graph. What does the graph of the function -1 look like? Well, it's a flat line. So no matter how far to the left or right you go, the answer is always a -1. Okay, so there's two ways you could do it. One way is if you've taken the time to memorize this, the problems can be really fast. But L'Hopital works. So let's go ahead and do another problem. All right. Now once again, we have a polynomial over a polynomial, and we're doing a limit at infinity. Notice that the power on the top is less than the power on the bottom. When that happens, the answer is always 0. But once again, I'm using the shortcut. However, doing L'Hopital works as well, so let's pretend I don't know the shortcut. Plugging that into the top, we have -25 times infinity. That's going to be infinity. 25 times the number is infinity. And if I plug in negative infinity and square it, I get positive infinity. Positive infinity plus 25 is infinity, so once again, you can see we have L'Hopital. So I can do L'Hopital here. The derivative of the top is 25. The derivative of the bottom is 2x. Plugging in my answer here, I end up with -25 over -infinity. We don't care about the negatives, they cancel. And we said on our slide that when you have a number over infinity, which is what that is, the answer is 0. Okay, so that's the longer way and the shorter way. Let's take a look at one more example like this before we move on to a new set. Now in this case, we end up with the shortcut is not quite as helpful. In this case, we have a bigger power on the top and then on the bottom. And when that happens, when you're taking a limit at infinity, the answer is either plus infinity or negative infinity, but that's not really good enough. You have to say which one it is. You can't just put both. Okay, so our shortcut's not that helpful for this one. There's ways to do it, but my advice is in this case, it's probably just going to be easier if you just do L'Hopital. Okay, so plugging in infinity to the top, if you raise negative infinity to the 4th power, you're going to get a positive infinity. We'll have the negative in the front of the fraction. Plugging in negative infinity on the bottom, when you square, it becomes positive. If you multiply positive infinity by 2, you get infinity. If you take 1 away from a positive infinity, it's still infinity, and we still have a L'Hopital situation here. So we don't put equals. That was a no-no, Mr. Yields. We don't put equals. All right. So we do L'Hopital. We take the derivative of the top, which is going to be 4x cubed. We take the derivative of the bottom, which is 4x, and we can reduce that. Fours cancel, and x goes into x cubed squared, x squared times that. Now, if I plug it in, here's what I get. I get negative infinity squared. Or sorry, negative infinity squared. So when you square a negative infinity, you get a positive infinity with a negative in front of it. So now we see the answer is negative infinity. So the shortcut's not quite as helpful when the number on the top is bigger than the number on the bottom, because it gives you one of two possibilities, which is nice on a multiple choice test, because if they only have one or the other, then you know which one to pick. But a lot of times it's kind of nice to just know L'Hopital. We already did that one. All right. We're going to be applying the same principles here, but it's going to involve limits at infinity, but just with e and ln instead. So once again, you know, like with all limit questions, you always start with direct substitution. Now, 1 over infinity is 0, and e to the 0 is 1, and so we have our answer. All done. Nice and easy, right? How do I know that that's 0? Well, in case you guys forgot, I gave you this little chart earlier. We filled in all these values. So if you missed that, you might want to rewind the video to where we talked about that. Get those values. Those are kind of important. And once again, these are great things to throw in a flashcard, which, by the way, I already have for you. They're on Google Classroom. All right, next. So for this one, we're going to do our direct substitution. Now, negative 3 times negative infinity is positive infinity. Now, e to the infinity, we talked about that earlier. Bring up the slide to show you guys. E to the infinity, that's this thing here. If you plug in here, you get e to the infinity. E to the infinity is infinity. So, if you have a negative infinity and you take 3 away from it, you just get negative. Another one here. Plug in your infinity. Direct substitute. Now, first of all, what's ln of infinity? About it earlier. ln at infinity is infinity. So, the top is infinity. The bottom is. And infinity cubed is just infinity again. Uh-oh, we have a L'Hopital situation here, don't we? So, here's how we have to handle this. First thing we're going to do is we're going to take the limit and we're going to do each piece separately, because part of that expression was L'Hopital, part of it was not. This part of it was L'Hopital. This part was not. So we're going to have to treat those separately. Okay. Now we already know what the limit of 2 is at infinity, a constant function. We take the limit of a constant function at infinity, it's just the number itself, just 2. But this guy, we ended up with getting infinity over infinity. That was a L'Hopital situation. So let's do the derivative of the top, which is 1 over x. Well, I guess I'll write it down. The derivative of ln of x is 1 over x. Negative stays because it was there to begin with. And then the derivative of the bottom is 3x squared. Now what I'm going to do here is I'm going to have to simplify this complex fraction. We don't like complex fractions when we're doing limits in calculus, so we simplify them. So I'm going to multiply the top and the bottom by x. That leaves me with the following. So we already took the limit of the 2, so I'm going to leave that separate, but now we're working on the limit of this. All right, now if we plug in infinity here, I get negative 1 over infinity cubed times 3 is going to be infinity. And 1 over infinity is 0. My final answer there will be negative 2. Do another one like that. Won't be too mind-blowing at this point, I don't think. If you plug in infinity, you get e to the infinity. E to the infinity is infinity. And infinity plus 5 is. Another one. Now this is with trig. Now with trig, things are a little bit different. We're going to, first of all, we probably should take the limit of these things separately, like we did last time. Avoid confusion. So we're going to find the limit of sine x over x. And we're going to add to that the limit Now this one, on the right side, that's easy. The answer is just 4. The top, if I plug in infinity to a sine functions wiggle. So as I go to the right and left, they never reach a limit. So we call that oscillating. And on the bottom, I get negative infinity. We talked about how when you have an oscillation with sine or cosine divided by infinity, the answer is 0. So this comes out to be 0 plus 4, which is this one. All right. If I plug in negative infinity here, I get an oscillation. Cosine just goes back and forth. So as x gets bigger and bigger, the function just keeps going up and down. And if I plug in up here, I get infinity. So I've got negative infinity divided by an oscillation. And when that happens, the limit just doesn't exist. And once again, how do I know that? I wrote it down in that little chart for you guys earlier. I'll bring it up again. If you missed that part, go back on the video, rewind until you get there and see what all this stuff is about. But infinity divided by an oscillation. Okay, number 16. All right. Now, there's a change in vocabulary here I want you guys to pay attention to. This is what we call an infinite limit. That is different than a limit at infinity. Those are different things. Okay, a limit at infinity is what we've been doing prior to this. It's when you have this, when the x is approaching infinity. An infinite limit is one where when you do the limit, you actually end up with an infinity as an answer. Some of our last problems were also infinite limits. I just didn't identify them as such. All right, so let's go ahead and see what's up with this thing here. So if you tried doing your direct substitution, you're going to get negative 4 over 0. That's undefined, right? There's no answer there. Now, technically, it's not wrong to say that the limit does not exist there, because that is true. But the problem is there's a few ways it could not exist. It could either be infinity, that's undefined, or negative infinity, that's also undefined. Or maybe it just doesn't exist. In other words, it's neither one of those. And the way that that works is when you're thinking of asymptotes. In this case, if you have both sides going up as you approach this line, that's infinity. If you have both sides going down as you approach that asymptote, it's negative infinity. But if you have one side going up and one side going down, that would be does not exist. So In this case, even though the limit is undefined, we want to be sure about what kind of undefinition it is. Now, the other thing you might notice is there's a little negative here. That means we are approaching from the left. Okay. Now, the only way that we're going to be able to get this is with a table. Okay, so, all right, so here's what I mean by approaching the value of -2 with a table. Now you're noticing that we're approaching -2, but from the left. I'm going to put -2 over here, and then I want to pick a number to the left of that, like negative, what's a number that's slightly smaller than -2? How about -2.001? Or number, and then a number even more small than, or even more negative than that would be this. Or how about this? So what's happening is we're getting closer and closer to -2 from the left. And as I get closer and closer to -2 from the left, we want to find out what are we reaching over here. It's undefined. But the question is, are these numbers getting bigger and bigger and bigger? Or are they getting smaller and smaller and smaller? Now, if this is a calculator question, then this is awesome because you can just plug the function into your calculator for the y1 value, and then go back to your home screen and plug in each one of these using parentheses and get your answers. Now that's what I'm going to do. If it's not a calculator question, I'll tell you what you do about it, but let's go ahead and do the calculator approach first. I'm going to pause the video here and calculate those. And here's what I got for this one. I got 22.05, and for here I got 202.005, and for the last one here I'm getting 2002.0005. So what's happening here is as I get closer and closer to -2, these numbers are getting bigger and bigger and bigger. So what infinity is it approaching? Positive infinity or negative infinity? The answer is positive infinity because the numbers are getting bigger and bigger as I approach -2 from the left. Now, let's say you didn't have your calculator. What would you do? That would kind of stink, honestly, because, I mean, still, what you could do is you could just do the one that's closest to 2 and see, do you get a really big number? And is it positive or negative? That would be pretty much all you need to do. But still, plugging in this number would really be very uncomfortable to do. It would take a lot of time. I don't think they would even give you a question like that unless they allowed you to have a calculator. To tell you the truth. Now, what's another thing though that you guys might want to be aware of for this problem? The other thing you might want to be aware is what if it wasn't a minus? What if it was a plus? Well, in that case, you'd plug in numbers that are to the right of it, like -1.999, or numbers like -1.99. And basically the way I do this is on the left side, I always take this number here and I subtract 0.001, and that gives me this. On this side, we add 0.001. Okay, and the next one is taking away 0.01, taking away 0.1, whereas over here it's adding 0.01 and then adding 0.1. So that's how I've always done it, and you can kind of see what's going on the left and right sides. If they didn't have anything here at all, like if it wasn't a plus or a minus, then what you'd have to do is look at it on both sides and see, are they both getting bigger and bigger on both sides, or are they getting smaller and smaller on both sides, or are they doing opposites? If they're doing the same thing, it's infinity. If not, then you would just say does not exist. Okay, so that's infinite limits. Your answer comes out to be infinity of some kind. Here's another one. So we're approaching 2 from the right. So for this one, I'm going to go through it a little bit quicker. We're going to approach this with a table. We don't really need to do a whole bunch of numbers. We really just need to do one. We're approaching 2, but this time we're coming at 2 from the right. So I'm going to add 1,000 to that. Now we know that this one's going to be undefined. That's going to be on the bottom. You get 0. So I'm going to plug 2.001 into this function, and I'll show you what we get. Now when I plug in 2.001, I get 1,000. Now that's a big positive number, and so we can conclude that this thing is approaching positive infinity. It's getting bigger and bigger in a positive direction. Okay. All right, let's talk about piecewise functions now. This question is asking us, what is the limit of f of x if my f of x function is a piecewise function? Notice what they want us to find the limit of is -1. That's the place where the two pieces are connecting. So now if there was a little minus here, that would mean we're approaching from the left and you would only use the top piece. If there was a plus, then that means we're approaching from the right, you'd only use the bottom piece. But since there isn't anything there, that means we're approaching from the left and the right. So to answer this question, we need to find the limit of f of x as x approaches -1 from the left, and we need to find the limit of f of x as x approaches -1 from the right. Now, if I'm approaching 1 from the left, like I said, we're going to use the top half. So if I plug in 1 into the top, I'm going to end up with, well, let me write it out first. That. And then if I'm approaching 1 from the right, we're going to use the bottom half. Now let's figure out what this equals. Direct substitution will give me -1 squared is 1 plus 1 is 2. And as for this one here, direct substitution, well, there's nowhere to plug it in, so the answer is just the number that's there. It's 2. They're equal. That means the limit exists. If the limit from the left and right are the same, that means the limit exists, and that's what the limit is. So the answer for that is 2. So with piecewise functions, you have to approach from the left and the right, unless it gives you a sign here to begin with, in which case you only do the one side they ask. And in order for that limit to exist, it has to be the same on the left and right if you're doing a double-sided normal limit. All right, let's talk about absolute value functions here. So what we talked about when finding limits or derivatives or integrals of piecewise functions, most of the time what you're going to end up doing is just changing it into a piecewise function. Okay, and the way you do that is you take the part that's inside the absolute value, you set it equal to 0, and you solve. And if you do that, you end up with x equals -2. You do a number line. And what you're going to do is you're going to be plugging in to -x plus 2 a test point. So if you plug in -1, will the absolute value signs, I think I wrote that wrong, back up a little bit. You're going to plug in a test point from this area. So -x minus 2. And in this case, I want to pick a number over here. So that would be like -3. Now, if I do -3 take away 2, will the absolute value signs change? Well, first of all, we have negative in the front, and then we're plugging in a -3. So double negatives makes a positive. So we have 3 take away 2, which is 1. Will the absolute value sign, bars change 1's sign? The answer is no. So there's no change on this side. What about if we plugged in a number over here, like 0, for instance? Well, negative 0 take away 2 is negative 2. The absolute value bars will change the signs. So that means that for anything to the left, for all values of x that are less than negative 2, there will be no change. But for all values of x that are greater than negative 2, there will be a change. And so what we're going to do is we're going to rewrite this expression to look like this. You're going to write the same function twice. But one is going to be for where x is less than negative 2, and one where x is greater than negative 2. One of them has to equal negative 2. It doesn't matter which one you make equal to negative 2. And we decided that for x less than negative 2, there will be no change. And for x greater than negative 2, there will be a change. So we're going to change the signs on the bottom there. Okay. Now, before we go any further, I want to show you that we're going to rewrite these expressions a little bit. On the top, I'm going to factor out a negative 2. On the bottom, I'm going to factor out a negative 1, which means those cancel. Same thing's going to happen with this other one here on the bottom. I'm going to take out a negative 2. And on the bottom, I'm going to take out a negative 1. Now, there's already a negative in the front, right? So if I take out a negative 1, I've got a double negative. And the top one here is for that. The bottom one is for where it was greater than. Now, these can be simplified. Negative 2 over 2 is 2. And negative 2 over 1 is negative 2. I want to find the limit of this now as we approach negative 2 from the right. So let's back up a little bit and review what we just did. So first of all, anytime you're doing limits, derivatives, or integrals with piecewise functions, a lot of times you're going to want to change them into limits, derivatives, or integrals of absolute value functions. A lot of times you're going to want to change them into a piecewise function first. And this is how you do that. Now this was a little bit of a fancy move here where I had to simplify it, but that's an idiosyncrasy of these types of problems to be aware of. Now that we've rewritten this absolute value as a piecewise function, now we can do it. If I'm approaching 2 from the right, which piece do I use? You would use the bottom piece. The bottom piece is negative 2. And since this is just a constant function, no matter what you're approaching, the answer is that. So the answer is negative 2. Okay. Let's go ahead and move along here. Go ahead and take a look at step functions. Step functions are going to be solved with a table. Okay. In case you forgot what a step function is, a step function is something like this, where if you have, let's say I have this really quick. If you were to plug in 1.5, what a step function does is it takes this number and it rounds it down to the nearest integer. What's the nearest integer to 1.5 that is lower than that? Well, the answer is 1. Do another example here. What about 2.77? Well, that would be, what's the nearest integer that's less than 2.77? The answer is 2. Gotta watch out for negatives, though. Check this out. What if I gave you negative 1.5? What's the nearest integer that's less than negative 1.5? That answer would be negative 2. Because remember, negatives go in the opposite direction. That's what a step function is, right? Now, for this particular problem, if you were to plug in -3, it's not going to be very informative. You're just going to get 4. But here's the problem. The step functions are not continuous at integers. When you graph them, they look like this. They stay at one number until they get to an integer like 1, and then they jump up to another one. And then at 2, they jump up to another one, and they jump. So since we're trying to find a limit of a step function at an integer, the limit's not going to exist. Now, but I want to show you why the limit doesn't exist by using a table, okay? So, and the table is something that would be very helpful because I wonder, I'm not sure what you guys have on your worksheet, but if you have a plus here or a minus, it's one-sided, then that limit does exist. And this is how you would do it. So make sure you guys pay attention to the table. So here's how I would do the table. Call the function f of x here. Now I'm approaching -3. But it's going to be doing different things on the left than it is on the right. So give me a number that's to the left of -3. Hopefully you guys are thinking of like maybe 3.001. And then pick a number to the right, which would be -2.99. Now let's see what we would get if we plug these things in to our function. At 3 we end up with 4 as our answer, right? We've already figured that out. We plugged in -3 and we got 4. What if I plugged in -3.001? So let's try that. So negative 3.001 plus 1. Double negatives cancel, and I end up with 4.001. Now what is the closest integer to this that's less than that? The answer is 4. So over here we have 4. But let's plug in -2.99 as well. So if I do that, I think I'll just take a shortcut here. The double negatives cancel, right? And that's going to give me 3.999. Now, what is the closest integer that is to this number that's less than that? And the answer is 3. So the question, if I were to add, so you guys can see why the limit doesn't exist, because as I approach it from the left and as I approach it from the right, I get different numbers. They're not approaching the same value. They're approaching different numbers. So the limit from the left and right are not the same. But if I asked you what's the limit of -3 as I approach from the right, your answer would be 3. If I asked you what is your limit as we approach -3 from the left, your answer would be 4. So you have to pay attention to whether you're finding from left or right or just doing the whole limit. In this case, we were doing the whole limit. So since the limit from the left and right were not the same, we would just say the final answer is does not exist. All right, here's another type of question you guys will want to be aware of here. These are pretty common actually on the AP exam. Multiple choice. We're not doing a lot of multiple choice questions this year because the pandemic. We're really only doing FRQs, but who knows? They might put something like this in there, so we want to be ready. But like I said, this is more common as a multiple choice question. Anyway, find the value of k that makes this function continuous. So remember, for a function to be continuous, it has to exist at the point, and the limit has to exist, and then those two things have to be the same. So this is a quadratic, and this is a linear. They're always continuous. The question is, are they linking up at a common point? First of all, let's see if the function even exists at 1. If it equals 1, we're going to use the bottom piece. Oh, I forgot my minus 1. So the answer is actually going to be 4. Okay, so the answer is yes, it exists. But now we have to do the limit. Does the limit of this function exist? Now when it comes to piecewise functions, we want to know, does the limit exist at 1 to see if it's continuous? So to do that, we need to know what is the limit as x approaches 1 from the left, and is it equal to the limit as x approaches 1 from the right? Now, if we're approaching 1 from the left, that would be the top piece. If we're approaching 1 from the right, we would be using the bottom piece. Now, direct substitution here will give us the following. We end up with 1 plus k times 1 plus 3. Doing direct substitution over here, we get 4. Simplifying the left side, we end up with this, k plus 4. The right side is simple enough already. So the question is, what value of k will make this function continuous for all values of x? Well, it's continuous if these two limits are equal, and those two limits will be equal if k plus 4 equals 4. That means that k would have to equal 0. And there's your final answer. So you don't really need to do this part. I just want to remind you of what continuity requires. However, all you really need to do is set the left side equal to the right side, plug in your number, and solve. Okay? Let's go ahead and continue. Okay, this says 32, but I know in your guys' worksheet that's not what 32 looks like, or your next question equals. So we're going to switch gears here. I have another worksheet. Now for you guys, your numbers 23 through 30 are questions like this. Now they're not exactly matched exactly the same on here, but I'm just going to do a whole bunch of different problems and you guys can kind of get a feel. So we have a graph here. Some stuff I want you guys to be aware of is that there is a horizontal asymptote here and a vertical asymptote here. Okay, now let's go ahead and jump in and do some problems. So what is the limit of the j function as x approaches 0 from the right? So here's my j function, and we're approaching 0 from the right. So I'm going down this way. I'm trying to get to x equals 0, and as I do, the graph is just dropping down lower and lower. So we would say the answer to that one is negative infinity. Okay, let's go ahead and take a look at the next one. What about if I'm approaching 0 from the left on the j function? Now, as I approach it from the left, I actually am landing at a number there, and the answer is 2. Now, same thing. What if I'm approaching 0, but this time on the k function from the right? Well, if I'm approaching 0 from the right, it bends up and starts to get closer and closer here to 0. But if I'm approaching 0 in general, I'm sorry, I put the answer in the wrong spot. Let me back up. 0 goes here. What if I'm approaching 0 from the left? That would be 2. But what's the limit of k of x at 0? That means from the left and right. Well, that only exists if they're the same, and they're not. One was 0, the other's 2. So what we would say there is that the limit does not exist. Let's take a look at the next one here. What's the limit of j of x as x goes to negative infinity? That means as I go to the left forever, what limit is it approaching? What y value? Well, it's reaching this horizontal asymptote, which is about y value of 3. What about as we do take the limit of j of x as x goes to infinity? In other words, as x goes off to the right forever. Well, it just gets higher and higher and higher. And so the answer to that one's infinity. This is a little bit of a different type of question here. This is where we get to use the properties. The limit of j of x and k of x as x approaches 2. Basically, you're just going to find the limit of j of x at 2 the limit of k of x at 2, and you're going to multiply them. So what's the limit of j of x at 2? In other words, what y value is it reaching at x equals 2? And the answer is 4. And what y value is k of x approaching as x approaches 2? It's reaching a value of 6. So that answer would be 24. Take a look at another one here. What is the limit of j of x as x is approaching 4? Okay, now there's no point there. But that doesn't mean the limit doesn't exist. That means that the function's value is not at this point. But it does mean that, but as you can see, whether I approach from the left or from the right, either way, they're converging at this point, and that's the limit. So the answer to that one is 6. But that's not the same thing as j of 4. J of 4 is not what is it approaching, but what does j actually equal at 4? And that's this solid dot down here, so that answer is 2. How about for number 18? Now, when you're finding the limit of a composite function, what you're going to do is you're going to take that limit and you're going to slide the limit to the inside, because the first part it's going to affect is the inside. So we really want to find what is the limit of k of x as x approaches 1 first. What is the limit of k of x as x approaches 1? In other words, what y value is it approaching? And the answer is 3. So we're just going to plug in 3 there, and j of 3 right there is 5. So there's our answer. Take a look at another one. Same thing on number 19. We're going to start by taking that limit and sliding it to the inside piece. Approaching negative infinity of the j function. All right, so what is the limit of j of x as x goes to negative infinity? Well, we already talked about that back here on this one. As we go off to negative infinity, it's approaching 3. So this becomes 3. K of 3, right about here, and that's a value of 4. So that would be our answer for that one. Let's take a look at another one here. So for this one, we're finding the limit. We're going to take our limit, and we're going to slide it to the inside piece like we have been, right? So it's going to be j of the limit as x approaches negative 2 from the right of the k function. So from approaching negative 2 from the right, we're approaching 0. But this is when you're doing directional limits, in other words, you're coming from a particular direction, that could change the outcome of something. Let's see. Here's what I don't want you guys to think. As we're approaching negative 2 from the right, okay, it's going to 0, right? So you might think this, what's j of 0? And oh, j of 0 is 2. Well, that's actually wrong. Now, let me show you. Well, maybe it's wrong, maybe it's not, but let me show you why that's not exactly a perfect way of thinking about this. You're right. This is the limit of k of x as x approaches negative 2 from the right is 0, but it's not 0, it's approaching 0. Okay, now let me ask you, is it approaching 0 from numbers that are bigger than 0 or less than 0? Well, since it's coming from underneath, it's coming from numbers that are less than 0, so that's like it's approaching 0 from the left. Okay, so I don't want you guys to find j of 0. I want you guys to find what is j approaching as x approaches 0 from the left. Now, as we approach 0 from the left, the answer is actually negative infinity. I'm going to ask you the same question, but this time instead of approaching 2 from the right, I'm going to approach it from the left. Watch what happens. So once again, you're going to take your limit, you're going to slide it to the inside, so that's going to look like this. The limit as x approaches negative 2 from the left. K of x. Now, I'm approaching negative 2 from the left. That means I'm coming this way, right? Once again, it's just going to be 0. But this time I'm coming at 0 from above 0, which is kind of like you're coming at it from the right, so to speak, if you're thinking in terms of x. Coming from numbers that are bigger than 0 would be like coming at it from the right. So now I'm approaching 0 from the right on the j function. So if I approach 0 from the right, we actually end up with 2. So depending on what direction you're coming from, that will determine the outcome. Okay. All right. One more topic to talk about here. Gotta jump way up high here. Passed all this stuff a while ago. Okay. Let's talk about this one. This is the second fundamental theorem of calculus. Now, when you have this is what we call an integral function. When your integral function has just a number down here and just an x right here, and you're being asked to find the derivative of your function, well, it's pretty easy actually. All they're asking you to do is find the derivative of your function, right? Now, the derivative of f of x is f prime of x, and that's what we're trying to find, right? And in this case over here, the derivative of an integral, they just cancel each other out. Now, for reasons that I'll show you on the next problem, you end up just basically with this expression here, but instead of t's, you're going to have x's. Now, I'll explain why the variable changes in a minute, but for now, there's your answer. So here's your nice little shortcut. You do not have to show all that work. That's a lot of extra work. If you want to find the derivative of an integral function, so long as there's just a number here and x here, basically your answer is just going to be this thing, but with x's instead. We talked about that. And the reason for that basically is because derivatives cancel integrals. So if you have an integral function, you take the derivative of it, the integral's away, and you're just left with the integrand. But there's actually a more general rule, which is going to will help us understand why there's x's in there in the first place, and it will also help us understand how to do a problem like this. So let me go ahead and talk to you guys about how to do this one. So let's say, for instance, that we have a function that's an integral function of like that. Well, let's be a little bit more broad this time. Let's say that it's not just a number on the bottom, but let's say there's actually a function down here and a function up here. Okay. Now here's how we talked about this before. Notice this is little f and this is big F. This is the derivative of this. Okay. So let's go ahead and say that the integral of little f, right, is big F, right? So the first thing I want you guys to understand is that this can be rewritten like this. Right? And then this can be written like this because of the first fundamental theorem of calculus. Plug them in and subtract them, right? But here's the thing. The problem is actually asking us to find the derivative. Derivative symbol there. All right, but there's a chain rule here, isn't there? So we do the derivative of the outside. Now the derivative of big F is little f. And we multiply that by the derivative of the inside. Derivative of the big F is little f. And we multiply that by the derivative of the inside. So that's kind of the process that we're going to go through here. But what's important to notice is that the little f is what our integrand originally was. We integrated it so it became big F, but when we took the derivative, the big F just went back to being little f again. So your final answer doesn't have the big F in it at all. Okay? So, if we follow that pattern, then what we have is the following. We have little f, which is the integrand, and plugged into it is the b function. Times the derivative of the b function minus the little f function again, but this time with the a function plugged into it, multiplied by the derivative of the a function, which is 0. Now in this case, since the a is 0, that whole piece is just going to go away. And so here's what we would end up with as our final answer. They would usually put the 3x squared in the front times 2e to the x cubed minus 2. And then we could multiply the 2 and the 3 and probably just get this. But basically, if you have this set up, this is how you're going to get the answer. So it's the integrand with the upper limit plugged in, multiplied by the derivative of the upper limit, minus the integrand with the lower limit plugged into it, multiplied by the derivative of the lower limit. Okay? And just in case you want to see another example, I'll do one more like that just to kind of keep you guys up to par. It's a little bit of a confusing rule, but I'll show you one more example real quick here. Matter of fact, I think I'll even make it a little bit harder this time. Instead of negative pi, I think I'll just put like x squared. Okay, so let's remember. So the process that we had was that, if big F is a little f, right? The outcome is going to be little f with the upper limit plugged into it, multiplied by the derivative of the upper limit, minus the little f with the lower limit plugged into it, multiplied by the derivative of the lower limit. Okay? So this is your b, this is your a, and this is your little f. Okay, so let's do that. So it's little f with b plugged in times the derivative of b minus little f with a plugged into it multiplied by the derivative of a. And if I multiply this times 2, I'm going to get negative 6 sine x cubed minus, if I multiply this by this, I'm going to get negative 4x, but there's also a minus there, so it becomes plus 4x sine x squared. Okay, and that's the second fundamental theorem of calculus. Okay, and that's